Good morning. I could not upload the lectures number 15 for the last 2 or 3 weeks. This is because that there was unavoidable circumstances for me. Moreover, I would like to prepare another lecture series for undergraduate student on basic crystallography and solid materials. So I planned that AS and A-level chemistry lecture series now on will be uploaded every 2 weeks instead of every week. I hope the students of undergraduate classes will enjoy the lecture series of basic crystallography and solid materials, though it is a course on the last and final semester on undergraduate program, but student of undergraduate program, any level, hopefully will enjoy that lecture series. Now I start the 15th lecture of AS and A-level chemistry lecture series. This is the slide which I didn't mention in the redox reaction, and this is an interesting slide to show the various oxidation stage and also naming of inorganic materials. You see, this one, here nitrogen in oxidation state 3. So we call this compound systematically, not traditionally, systematically as nitrogen, as sodium 3 nitrate. And then the same compound, you see, it's also, if we call it in a systematic way, then we call sodium nitrate 5. And why it is? Because you can see that oxidation state of nitrogen here is 5 and oxidation state of nitrogen here is 3. But traditionally it is called nitrogen, sodium nitrite and sodium nitrate. Next one is a oxidation state of bromine. We can see bromine can have very many oxidation states. So elemental bromine, we know it has oxidation state 0, but bromide ion, we can have a hydrogen bromide compound. Here bromine has an oxidation state -1. And if we got bromate ion, here oxidation state of bromine is +1. And if we go there, that is bromate ion again, its oxidation state of bromine is +5. So this is a example of an element having different oxidation state. And I would like to mention that the compound I'm mentioning, there are naturally occurring compound, either synthetically or naturally available. Here, an element from lithium to neon and sodium to chlorine. We can see the oxidation state of or oxidation numbers in oxides of this element and oxidation number in hydrides of these elements. So lithium can form only one oxide and one hydride, whereas beryllium also can form only one oxide or one hydride. And therefore, as lithium is having always +1 oxidation state, and beryllium having always +2 oxidation state, boron also can form oxide and hydride. But mind that the elemental form of all these elements oxidation state is 0. That's what we know from other lectures. So here we can show how many oxidation state an element can have. For example, carbon, it can have an oxidation state of -4 as well as oxidation state of +2 and oxidation state of +4. Nitrogen, this is one of the elements which has got lots of oxidation state compound available. Nitrogen can have -3 oxidation state, +1, +2, +3, +4, and +5, and so on. So I have written all the chemical formula of these oxidation state compounds below. We know that we can also name it traditionally as well as with systematical naming. We discussed it in our lecture. So here is lithium-1 oxide, beryllium-2 oxide, boron-3 oxide. Similarly, lithium-1 hydride, beryllium-2 hydride, and boron-3 hydride. But we can borohydride, beryllium hydride, lithium hydride. This is the traditional name. Many chemists prefer these oxides to be named as traditional. For example, we call it hydrogen sulfide, phosphine, in hydrides of phosphorus and hydrides of sulfur. We go to next lecture. Now we are taking another chapter of AS level, that is states of matter. This is what I can show you, states of matter of, or 3 states of matter, that is gas, liquid, and ice. If you look to this, the molecule in gas are far apart from each other. If you look to this, molecule in liquid is not that far. Solid is very regularly arranged. So if we, from this slide, if we define this gas, liquid, and solid, these 3 states of matter. So gas, you see, it has got no fixed shape or volume. Molecules in gas that are far apart. Molecule in gas can be compressed, and those can move freely from place to place in all directions. Liquids, shape, it takes the shape of the container, and molecules in liquids are close together, not far apart as gas. Liquid have fixed volume, and it can be compressed slightly than compared to gas. And molecules are arranged randomly and free movement in all directions. It's solid, we have fixed shape and volume. And the particle, that means molecules in atoms or molecules in solids, are touching each other, that is, they are compact. And their atoms cannot move around from its position. It can vibrate when we supply energy from its own position. Another matter, which we call liquid crystal, this is not in the syllabus of A level, but just to define that the liquid crystalline metaphase, I just mentioned this one. We can see there are some compound which when you melt it, it forms a cloudy state first. And then on increasing temperature further, this cloudy state becomes liquid. So the cloudy state between liquid is also a solid metaphase, and that is called liquid crystal metaphase. This is another state of matter, but this is not in the syllabus of A level. We go to gaseous state. The gaseous state, kinetic theory of gases. We have to have few assumptions for this kinetic theory of gases. For example, we have to say gas molecules move rapidly and randomly. That assumption we have to make. And then the diameter of molecules in the gas is compared to the volume of the gas is very little, hardly any volume of the molecules. That we have to also consider assumption. And then intermolecular force of attraction or repulsion between the molecules in gaseous state are almost nil. The collision are elastic, which means no kinetic energy is lost in collisions. The temperature of gas is related to the average kinetic energy of the molecules. And this condition, if we fulfill, then we call it an ideal gas. But in reality, we do not have ideal gases. Only helium and neon behave very closely to ideal gases. Rest are real gas. In this state of matter, we will discuss only ideal gas, and real gas discussion is in A-level syllabus, not AS level syllabus. We will come to it later in some other lecture. You see, volume of gas depends on its pressure, which is measured in Pascal, its temperature, which is measured in Kelvin, number of moles of the gas. So at constant temperature, the volume of gas is inversely proportional to its pressure. This is what is Boyle's law. If we take the next slide, at constant pressure, as the temperature of gas increases, the volume of gas is directly proportional to its temperature. This is what is Charles' law. That is, at constant pressure, volume of gas directly proportional to temperature. This is what we call Charles' law. Similarly, we can say about Avogadro's law. What it is? At constant temperature and pressure, the number of moles is directly proportional to its volume. This is Avogadro's law. If we take this mathematically, the same thing what I say, that is Boyle's law, volume is inversely proportional to its pressure when temperature and number of moles constant, which we say PB is equal to constant. Similarly, Charles' law, volume is directly proportional to temperature, which when pressure and number of moles constant. That is, volume is equal to constant in temperature, or V by T is equal to constant. Avogadro's law, volume is directly proportional to number of moles when pressure and temperature are constant. So V is equal to constant into N, which is number of moles, or that is V by N is equal to constant. If we put all these laws together, we come out with an ideal gas equation. What is? Then volume is proportional to, directly proportional to N into T, and inversely proportional to pressure. Using a proportionality constant R, we can read it as V is equal to R into R, N T by P. So we come out with PB is equal to nRT. So remember that when we solve any problem on ideal gas flow, we have to write the unit of different parameters precisely. If we do not consider properly the units of the parameters, our calculation will be wrong. That's what we have to remember always. So we can find out any of the five physical quantities of ideal gas? No, if we know the 4 physical quantities. And we have to remember very well that the correct units to be used in the calculation. If not, then we get wrong result. Remember that we get often temperature in Celsius. We have to make it in Kelvin. So 273 plus the Celsius temperature gets it, we convert it in Kelvin. Similarly, 1 atmosphere is equal to 101,325 pascals. We have to convert pressure in Pascal, but in many problems we see that it is given in kilopascal. So that's what we have to remember. And the gas constant is given as 8.31 joules per Kelvin per mole. That's what we have to remember. But be sure that this is all the 4 parameters will be given to get the 5th parameter of the ideal gas equation. We take a problem now. We see it says calculate the volume occupied by 0.5 mole of carbon dioxide at pressure of 150 kilopascal at a temperature of 19 degrees Celsius, and gas constant is also provided in the problem. So what we have to do now, find out the parameters given and its proper unit. So in the problem, the volume is given at 4.5 mole carbon dioxide gas. So, and the pressure is given. We are asked to calculate the volume. The pressure is given, temperature is given, and number of moles is given, gas constant is given. So we have pressure, temperature, number of moles, and gas constant. So you have to make sure that it is in correct unit. So pressure is 150 kilopascals, means 150,000 pascal. Temperature 19 degrees Celsius means 273 plus 19, that is 292 Kelvin. Number of moles is 0.5 mole. So if we rearrange and find out the volume, then we rearrange the ideal gas equation like V is equal to nRT by P, and put all the given values, and we come out that the volume of the gas in the problem is 8.09 in 10 to the power minus 3 per cubic meter, 10 to the power minus 3 cubic meter. Second problem is this, and with this second problems we finish our lecture, which I have given almost more than 20 minutes or so. So that will be the last slide for the 15th lecture. It is given the volume of a flask and then mass of the oxygen gas, and we are asked to calculate the pressure exerted at a temperature of 120 degrees Celsius. Gas constant is given and molecular mass of oxygen is given. So as I say, we have to rearrange all this and properly make sure that the proper unit is given. So 127 degrees Celsius is equal to 400 degree Kelvin. So we convert it into Kelvin. Volume is 5.00 dm cube, and if we convert it in meter cube, then it is 5.00 into 10 to the power minus 3 meter cube. And the number of moles we have to calculate. The number of moles we can calculate the mass by divided by relative molecular mass. So 4 gram is the mass, and divided by 32, the relative molecular mass of oxygen, it comes out to be 0.125. And then we rearrange the ideal gas equation and find out the pressure. So pressure is equal to nRT by volume. Put all the values given in the problem, and then we come out that the pressure for this gas, 4 gram of gas, is equal to 8.31 into 10 to the power 4 Pascal. 8.31 into 10 to the power 4 Pascal. With this, I would like to finish the 15th lecture, and we will continue the 16th lecture, as I said, in 2 weeks again. Thank you very much.